So, regression. So, as I said earlier in the first video, the first part of the method, which is the estimation part, which is the methodology 5, this is where we are now, the methodology 5, the estimation part. So we want to estimate our parameters. So that's why we need the regression model. So what exactly is this regression model? So it is basically we studying the dependence of one variable, which is the dependent variable, on one or more of other variables. We have other variables. It can be one, that's the explanatory variable. It can be one, it can be more than one. So we just want to look at the dependence of this variable on other variables, because a particular variable, mostly represented by y, it's always depending on some other variables, mostly represented by x. Now if they are more than one, that's when we represent them with x1, x2, x3. So for example, when we have a very popular example is when we have the demand function. So the demand function, the quantity demanded, Q, is majorly dependent on the price. So our y here is the Q, which is the dependent variable. It's dependent on the price. It's when you know the price, that's when you now know how many quantity you will need. So the quantity, for you to know your quantity demanded, for you to know your Q, you have to depend on what the price is. So but we have other factors that might affect quantity demanded, like income. Let me just use I to represent income. So if we put income also in this model, that means we have two explanatory variables explaining this quantity demanded. But we know the typical demand, just assume every other one is constant, then we now pick price. But if we want to put more variables that are actually explaining our dependent variable Q, we will have something like price, income, taste, and so on. So these are the explanatory variables. They are explaining this dependence variable. This one depends on them. They are explaining this dependence variable. So in a regression, that is what we want to do. We want to study the dependence of this Q or Y on all the explanatory variables, either one or more. We want to see the relationship between them. Now, while doing this, we use sample regression function and population regression function, which I'll still explain very soon in a future video. Now, one of the founder of this regression model, called Francis Galton, he studied regression. He studied this regression using the height of people. He noticed that the height of people that he's studying of a family, the height of people in the family, let's say children in the family, the average height is moving towards the average height of the population. Okay, let me just give an example. Let's assume this is the population. We have a population like this. And everyone in that population have different heights. Let's say this one is 6 feet tall. This guy is 7. Another one is 6. Another one is 5. Another one is 8. Another one is 7. Another one is 6, and so on like that. Now when we find the average height of the entire population, let's assume we get something like 6.2 as the average height of the entire population. So Galton now realized that if he decides to pick a family, let's say a family in a particular population, a family that have just 2 kids among this population, he realized that by the time he checked the age of the height of these 2 families, the average height of the 2 kids in the family is moving towards this 6.2 average height of the whole population. So let's assume the 2 kids, their average height, when you find the mean of their height, the mean of their height is like 5.8. Dalton will be expecting that the next kid that this family will be giving birth to will have a height that might be taller than this other two. Why? Because he has noticed that the height of the population, which is 6.2, the height of any sample like a family is moving towards that 6.2. So you'll be expecting that this person's height may either be, let's say, 6 or so, or 7, so that by the time they find the mean of these three, it's going to increase to something like 6 or 6.1. So you realize that each family, their height are moving, the average height of people in the members of the family is moving towards the population. So you now use the word is regressing towards the population. So this will be our basic concept that will help us to understand what the difference between sample regression function and population regression function. So that being said, let's continue with the nature of regression. Now this is a scatter diagram, this is scatter plot. So scatter plot is just trying to show us what exactly we mean by this regression. We are representing it on a graph. We have all drawn graph at one point or the other, but we notice that many times when we are drawing a graph, like a linear graph, we always have a point like this. So we will not have our line like this. That's a linear graph. And we also have some type of linear graph that are like this. And we also have quadratic graph, that one that is always curvy. Yeah, we also have so many other graphs. Some graphs are like this, some graphs are like this, some graph, we have so many different graphs. But the issue here is not that this type of graph, many of them, they like follow a pattern, so it's easier for you to connect the dots together in many of these graphs. But when we are talking about regression, it's much more difficult to connect the dots, because in a regression we have scatter plots. We are looking at people of different height. For example, many times it's going to form something that we call a scatter plot, to the extent that there's no way you can get a perfect curve like this, a perfect line like this, a perfect curve like this by connecting the dots. So for example, if you look at this, how do you want to connect this dot? How do you want to connect this dot that is going to make sense? So we are now trying to look at a particular straight line that will, as much as possible, represent all these dots. Yeah, we are very sure that it is not possible for the straight line to touch all the dots. We are looking at that particular straight line that will at least represent a straight line that is supposed to touch each of the dots. So that's exactly what we did here, this straight line here. Now we know that it has touched some dots actually, but there are some dots that is not touching, that is not representing. So we now look at the difference between each of the dots that it is not touching to the straight line. That is where our error term comes from, the disturbance term, the error term. Trying to show that yes, there are still some dots that are not being explained by this our straight line. The straight line is representing our regression function y is equal to beta 0, beta plus blah blah blah. So most of our graph, they are always like straight curve, because they do not look at all other error terms. They do not look at all the errors, all of that. They just assume all other ones are constant. They assume that they do not exist. Let me just use something like that. They just assume that they are constant, they are not changing, for example. So that's why you will always see a particular perfect curve, a particular curve like this, a particular curve like that, because they did not put all those error terms into consideration. But in regression, in econometrics generally, we put all this terms into consideration. So because of that, we cannot have a straight line that will touch all of them. We cannot have a perfect line that will touch all of them. So we now look for a line that best represents them. Then we now look at the error between all of them. So that's why in regression function we are always having the error term mu added to our function, trying to tell us that yes, there are still some dots that this particular function y is equal to beta 0 plus beta 1 x is not representing perfectly. So these are the errors. So that's exactly what this graph is trying to tell us. That's exactly what this particular graph is telling us. So that being said, let's look at some regression terminologies. The first one is the variables. We have the explanatory variables. We have the dependent variables. Dependent variable is our y, the one that is depending on the other one. Explanatory variable is our x. So those are the variables. They have different names that you can call them, different names, so you can just study that on your own. The parameters, aside from the variable, the parameters, in fact, they are like one of the most important things we are doing in this regression, because what we are estimating, the methodology 5 we are doing here, is actually estimating the parameters. We are estimating the parameters. So the parameters are the betas. This beta 1 and beta 2. In some instances, it's going to be beta 0 and beta 1, which I prefer to use. So you can use any one of the two. So beta 1 and beta 2. The beta can be more than 2. You can have beta 3 if you have like another explanatory variable. So, but all those betas, so they are basically our parameters. They are basically our parameters. Now, this beta is called the intercept or the constant. Intercept of the constant, because it's like fixed in nature. It's like fixed in nature. It does not have an explanatory variable here that can change it. And also, this particular one is called the slope. Beta 2 is called the slope. Now, in a particular econometric model, this is just like a general model, a deterministic model. They call many of the models that have so many assumptions deterministic, because they follow a particular pattern, they follow a particular system. But our econometric model, we always have the disturbance term, the error term, mu. So this particular econometric model will not just stop here. It's going to put mu, because it's putting into consideration those other parts that the determined or our economic theory is not explaining, that it is assuming to be constant, that is assuming to not be changing, that is assuming does not exist here, but in the real life, in the real world, they actually exist. So it's taking into consideration all those parts. So that being said, let's move on. So we move on to the we still continue with our terminologies. How this battery can carry me. So we continue with our terminologies. We want to look at linearity. Now we try to explain a particular type of regression function that is linear. Now we now have two different ways regression functions can be linear. It can be linear in parameters, it can be linear in variables. So like for example, this regression function is a linear function. How do we know if it's a linear function? If it's linear in variable, it simply means the greatest power of x is 1. Now if you look at x here is x is power 1, which is the same thing as x. So the greatest power of x will always be 1 for a function that is linear, and it will not be multiplied by another function. We cannot multiply this x by y. If we have xy here, it simply means that it's no more linear in variables, and we cannot multiply it by any other variables or divide it by any other variable like x divided by y. So that's a linear function that is linear in variables. And linear in parameters simply means the greatest power of your betas, any of the two, the greatest is also 1, and you cannot divide them by any other parameters like beta 1 here, or divide it by beta 2. So their greatest power is 1, and you cannot divide or multiply them by any other variables. So if they fulfill these two, it simply means they are linear in parameters or linear in variables. So we have two types of regression. We have the linear regression, also called the two variable regression or bivariate regression. We have the multiple regression. Now the linear regression, this is an example. It's also called the two variable regression. It's called the two variable regression basically because it has just two variables, one dependent variable and one explanatory variable. The multiple regression will also have a one dependent variable, but it may have many explanatory variables x1, x2, x3. In this particular study, in our course outline, we are not coming to multiple regression in any way, so we are just focusing on the linear regression model. So we are always focusing on two variables, one dependent variable and one explanatory variable. Now let's look at the PRF and SRF, the regression functions, the population regression functions and the linear regression function. Now, as I've explained earlier in the past videos and earlier in this video, our population is very impossible for us to estimate, to make decision with, because we are looking at men in Nigeria. For example, we are looking at millions of people. How can you be able to get data concerning accurate data about these millions of people and be able to work on it? It's impossible to do such a thing. So, but this particular population follow patterns. According to many of our economic theory, we already know the patterns, or we already have a clue of how the pattern is. When we talk about demand in a nation, now we already know the clue of how the pattern goes. So we mostly have a function representing our population, So this is an example of a population regression function, trying to show the relationship between the dependent variable y and independent variable x, with the mu, the error term, to put into consideration. We know that there are some errors that this explanatory variable, there are some parts that this explanatory variable will not explain in y, so this error term will explain it. So that's what the population regression function is. But since we now want to estimate, we want to know what b0 is, we want to know what b1 is. So this b0 is constant, trying to tell us that, okay, let's assume this our x1. Let's remove mu for now. Let's assume this our x1 is 0. It simply means our dependent variable will be our b0. This b1 is now showing the rate at which this guy is moving with this guy. The dependent variable is moving with the explanatory variable. So if b1 is I, let's say if b1 is 2, it simply means this guy, it simply means when our explanatory variable is at a particular number, this one will go times 2 higher before we now add it to this b0. So this particular one is explaining the rate at which this one is going, increasing or decreasing, while this one too is increasing or decreasing. So this we now want to estimate this b0 and b1. But as we have said, if we try to get data for the population, it is very impossible to estimate. So what we now do is we now go to a sample. Yes, we cannot get all the 100 million people, men in Nigeria. So why don't we just go to a particular community that they just have 200 men? Let's use those 200 to do our particular experiment. So suppose we want to look at the demand of the nation, we can just go to that community and look at the demand of that community. So that's our sample. So with that, we can now get a function for that community. We are now looking at how best can we now estimate the beta 0 and beta 1 of this function, that it will now represent this beta 0 and beta 1 of this population. So we are not picking the population, we are picking the sample, but yet we still want to use it to estimate, to represent this beta 0 and beta 1. We want to make sure that as much as possible, by the time we get the beta 0 and beta 1 of this sample, it will be equal to or almost equal to the beta 0 and beta 1 of this population. So that's what we are trying to do. Since we cannot study this because there are too many, we can study these people because they are small, but we want to ensure that it is representing the whole population, not just the community. Because when we get whatever decision we want to make, will not just be for the community, it will be probably for other communities too, and for the whole nation as a whole. So that's what this is now the sample regression function. This is the population regression function. So I mentioned here that we want to devise a rule or method that will make the sample regression function as close as possible without even knowing the population regression function. We want this b0 and b1 to be as close as possible to this b0 and b1. This b0 is the one that have at, the sample one have at. So we want it to be as close as possible to this B0 and B1 without even knowing what B0 and B1 is. For example, if I say this B0 is 3 and B1 is 4, and I want to tell you that okay, I want this B0 at and B1 at to be as close as this and this, you can easily be able to like look for mago way to make sure that okay, this one is like 2.9, this one is like 3.95, something like that. But we don't even know what B0 and B1 is. But we want this B0 at and B1 at to be as close as possible to these two, even without knowing them. So that's what we are actually doing in regression. That's what we are actually doing in regression. I think I'm just going to pause here. I think I'm going to pause here because my battery is critically low. Let me check. Can I still move on? Okay, let me check what we just have next. So estimation. So to estimate, we use this formula. Don't worry, I'll try as much as possible. Probably I'll use my phone to show the proving of all the formulas or many of the formulas. So this is the formula we use to estimate our beta 0. That means the sample one, beta 0 at and beta 1 at. This is for beta 0, beta 1 at. So for estimation of regression, we have two methods, the OLS and maximum likelihood. Don't worry, we are not doing this maximum likelihood, we are focusing on OLS. So, and these are the two formulas for estimation using OLS. So remove. Now the interpretation, I will encourage you to go and read the interpretation of your function. For example, if we have this function, how do you interpret this particular function? If you have this function, how do you interpret it? So we have different functionality of a function. We have linear function, meaning the dependent variable is linear. I've explained the meaning of linear, and the explanatory variable too is linear. That's lin. We have log lin. It means the dependent variable is in log form, the independent variable is in linear form. Lin log, it means the dependent variable is in linear form, the independent variable is in log form, and log, both of them, both dependent and independent variable, are in log form. So that's the difference between the four of them. These two, we call them semi-log form together. Called semi-log. Call them semi-log, the two of them. So how do you interpret? So I'll just take one as example without you can know how to interpret this. Well, you may not be able to know, though you have to like check your notes to read it, but I am actually doing this interpretation basically because of questions that you be asked, maybe 1B, 1C. They'll not ask you interpret your results. So most of the times it's always linear function they are asking us. So it's basically linear function you want to interpret. So how do you interpret the beta 0? You are just going to interpret it that okay, the value of the function, that means you mention the function, the value of this is beta 0 when x is equal to 0. Now take note, many times in the question they will give you what y is, what x is. You don't need to be using y and x. For example, they may tell you that okay, I think example that Mr. Bishi used, x is sales, y is sales revenue, x is advertisement. You don't need to mention x and y in your interpretation again. You are just going to say that when the value of sales revenue is now the function, the value of sales revenue is beta 0, whatever you get as your beta 0, probably get beta 0 as 10. The value of sales revenue is 10 when x, which is advertisement, when advertisement is 0. So the value of sales revenue is 10 when advertisement is 0. You don't need to see x and y. And for beta 1, how do you interpret beta 1? A unit increase in x, that's a unit increase in advertisement, on average will cause sales to increase by beta 1 if your beta 1 is 5 by 5. So you see a unit increase. So as I was saying, for beta 1, you just see a unit increase in sales revenue. On average, a unit increase in advertisement on average will cause sales revenue to increase by the value of beta 1, which is, for this example, we say 5. So that's the way you are going to interpret. That's just interpretation. I believe many of us should be able to like do the calculation aspects once you have the formula. So we are not going to be doing that particular part. So that's for the interpretation of your answers. So let's quickly look at the assumptions of OLS. let's see what we have in assumptions of OLS. We have the 10 basic ones, so I'm just going to like run through those 10 basic ones. So I'm not sure if the order is important, as in if assumption 1 should be assumption 1, because they kind of scatter it in different textbooks. So one of the first assumptions is that mu, the error term, is a random real variable. It simply means that the error term is probabilistic in nature. That means it happens by chance. It's not something that we can easily determine. It's not something that we can, it's not really systematic. It has probability features. That's the first assumption. All these assumptions, I basically think we need the meaning. For the symbolical representation, you just have to like check the textbook. Many of them are not difficult, they are like very short, so you can just check any of the material, Kusoyanis, Dugarati, Dr. Dio material, your notes for the symbolical representation. So because of time, I will just go into what they actually mean. So mu is a random real variable, trying to say that mu is probabilistic in nature. It has probability feature. Now the first one. The second one, the zero mean value of mu is either is the zero mean there is a zero mean value of mean, trying to say that mean has a mean value, mu has a mean value of 0, has a mean value of 0. Now what do we mean by that? Let me quickly go back to our graph that we drew when we are talking about regression. So this particular graph, remember I said that this line is trying to represent the whole scattered plot as much as possible, but yet all these parts are not staying on the line. These are the error terms. Now what that particular assumption is saying, that by the time you sum all these error terms together and you find the average, is going to be 0. That means by the time you sum everything together, let's just say is 0. When you sum all your errors together, the sum of all your errors should be 0. That's what this is saying. Yeah, although some of them may be large, some of them may be greater than 0, some of them may be larger than 0, some of them may be 1, some of them may be -1, some of them may be 2, but the sum of all your error terms should be 0. That's what this second assumption is talking about, that there is a zero mean value of mu, of the error term. So that's it here. So and the symbolical representation is expectation of mu given a value of x is 0. Now the next one is homoscedasticity. This simply means constant variance. What is the meaning of variance? Variance means spread. It's equal. It just means equal spread, constant spread. That's what homoscedasticity means, and the opposite is heteroscedasticity. Now what's this trying to say? This is trying to say that there should be a constant variance for your mu. So at each point, all those points that are not staying on the graph, all the points that are not on this particular regression line, their variances for all these error terms, their variances should be constant. That means they should have equal variance. All of them should have equal variance. That's what we mean by constant variance. Then the next one is normal distribution. Yeah, the distribution should be normal. That means it should be bell shape and with 0 mean and a constant variance, just like the continuation of this. It's going to have the mean of 0. So this normal distribution is more like the combination of these two. So it is normally distributed, it is bell shape with a mean of 0 and a variance that is constant, equal variance. That's normal distribution. Then the next one is it must lack autocorrelation. There must not be autocorrelation. There should not be autocorrelation between the distribution. So autocorrelation simply means that there should not be a correlation between a particular error term and another successive error term. If we have an error term we call ui and we have another error term we call ug, there should not be a correlation between these two error terms. If we have error term u1 and we have error term error term ut, and we have error term ut minus 1. There shouldn't be a correlation between the two of them. If there's a correlation between the two of them, we see that they are autocorrelating. That's autocorrelation. But this assumption is saying that there shouldn't be a correlation between a particular error term and another error term. That is autocorrelation. Now the next assumption is similar to this, but it is not this. If you look at autocorrelation, it's talking about two error terms. There shouldn't be a correlation between two error terms, successive error terms. But this other one, let's go there. This other one, zero covariance between an error term and explanatory variable, is talking about error term and explanatory variable. The first one is trying to talk about two error terms, but this one is talking about an error term and explanatory variable. It's trying to say that there shouldn't be a correlation between a particular error term and the explanatory variable. There shouldn't be a dependence relationship. That means the error term should not be depending on the explanatory variable directly or indirectly. So the error term should be stay on its own. There shouldn't be a relationship between that explanatory variable and the error term. So if we have an explanatory variable x, it should not be determined by the error term mu. So that's what this particular one is talking about. The first one, autocorrelation, is talking about two error terms, but this one is talking about an error term and explanatory variables. The next is that the explanatory variables are measured without error. Yeah, we should assume that when we are measuring our explanatory variable, they are error free. They are error free because any error that we assume it may have is carried by this mu. So we just assume x itself is error free because all the errors have been summed up to this mu. So we assume our explanatory variables are error free. Then the next one is perfect multicollinearity. So this is trying to say that there shouldn't be perfect multicollinearity, although there can be multicollinearity, but it shouldn't be perfect. What it simply means that there shouldn't be a perfect relationship, a perfect correlation between. When there is perfect correlation in our model, it simply means that there can be correlation. Yeah, it can be minimum, it can be small, it can be minimal, but it should not be perfect. It should not be perfect. One variable, one explanatory variable should not be perfectly explaining another perfectly. No, there can be a relationship because in a way most of it is almost impossible for us to say there shouldn't be a relationship between two explanatory variables. It's almost impossible because in a way the two explanatory variables might still work hand in hand, but it shouldn't be perfect. The relationship should not be perfect. That's multicollinearity. There should be relationship, but it shouldn't be perfect. That's multicollinearity. Now the next one is that the regression model is correctly specified. This is just like model specification, saying that we should specify our model correctly. We should make sure that our model is free from error of specification errors. So we are assuming that our models is free from specification errors. Then the last but not the least, macro variables should be correctly aggregated. Macro variables should be correctly aggregated. So those are our 10 assumptions of OLS. 10 assumptions of OLS. Now there are some that are related to the error time. I think the first 5 or first 6. So these are the first one. The error time is a random variable. There is zero mean value of error time. That is second. Homoscedasticity, that is equal variance for the error time, normally distributed. That's the 4. Then 5, autocorrelation. I think those 5. Okay, and this one to zero covariance between error time and explanatory variable. Those 6 are talking about the error time. In case the question says what are the assumptions that like relate to the error time, others do not like relate to the error time. So those are the 10 assumptions of OLS. So the last but not the least part of this video is OLS properties. What are the properties of OLS? This simply means what are the properties of OLS estimates, and what are the OLS estimates? Those are the betas, beta 0 and beta 1. So what are the properties of these estimates? The first is that they are linear. Remember the linear in parameter rule. It simply means that their highest power is raised to power 1 and they are not dividing or multiplying themselves. So that's linear rule. So they must be linear. The next is they must be unbiased. Yeah, the unbiased rule, we are still like going to prove it mathematically if you're able to buy enough time. So they must be unbiased, meaning that your estimated beta, both of your estimated beta, they must be representing your population itself, B0 and B1. So they should be equal or almost equal to your population, because that's what they are representing. So your estimated betas, your estimated parameters should be representing these population parameters. So that is the rule of unbiasedness. Then another property is that they must have the minimum or the least variance. They call this, that this make them become an efficient estimator. They must have the least variance. Your beta, your estimated beta, the estimated beta should have the least variance, the minimum variance. So that's what called make them the efficient estimator, and they must be consistent. So in short, all these properties, or the major theory properties, are summarized to something we call the blue, which makes them the best linear unbiased estimator. The linear is just for this, the unbiasedness is for this, the estimator, efficient estimator, that means minimum variance for this. So that's why they call them the blue, the best linear unbiased estimator. So those are the properties of OLS. Those are the properties of OLS. So I hope the next video will just be how to prove formula. I probably will end there. Time is against me.